Dear students, this is the first video from second chapter of Signals and Systems. In this video, we will cover Fourier series analysis and signal spectrum. The Fourier series is a representation of a periodic signal as an infinite weighted sum of sine and cosine waves, whose time periods are integer multiples of the fundamental time period of the periodic signal. Periodic signal can be represented using a Fourier series if and only if it satisfied following three important conditions known as Dirichlet conditions. According to the first condition, there must be a finite number of maxima and minima within one time period. The signal shown over here in this figure is a periodic in nature because it repeats after a time period of t0. We can also observe that the frequency of the signal increases to infinity within one time period. Hence, there are infinite number of maximas and minimas, and therefore, signal cannot be represented using Fourier series. According to the second condition, within one time period, there must be finite number of discontinuities. Signal shown in this second figure is also a periodic signal whose time period is t0. The amplitude of the signal reduces to zero in infinite number of steps of reducing sizes. Therefore, signal has infinite number of discontinuities within one time period. Hence, the signal cannot be represented using a Fourier series. According to the last condition, signal must be integrable over its time period. That means integration from 0 to t xt dt should be less than infinity. Signal tan of t, as shown in this figure, is a periodic signal whose amplitude ranges from minus infinity to plus infinity. Therefore, this is a non-integrable signal, and this is also a signal that cannot be represented using a Fourier series. Now let us examine a signal that satisfied all these three conditions. There is only one maxima and one minima within one time period, that is in accordance with the first condition. Secondly, there is one discontinuity within one time period, therefore it satisfies the second condition. And signal never reaches to infinity within one time period, therefore it is perfectly integrable within one time period. Hence, this is a signal that can be represented using Fourier series. Fourier series is named in the honor of a French mathematician, Jean-Baptiste Joseph Fourier, who made an important contribution in the study of the trigonometric series. The trigonometric Fourier series representation of a periodic signal xt with a fundamental time period of t is given as xt is equal to a0 plus summation for k is equal to 1 to infinity ak cos of k omega naught t plus bk sine of k omega naught t. Here omega naught is the fundamental frequency of the signal, which is given as 2 pi upon t. Here the coefficients are given as a0 is equal to 1 upon t integration from 0 to t x of t dt, and ak is equal to 2 upon t integration from 0 to t xt cos of k omega naught t dt. Similarly, bk is equal to 2 upon t integration from 0 to t xt sine of k omega naught t into dt. Now let us consider one practice problem from the previous examination. Here we are given a Sawtooth waveform as shown in this figure, and we are required to determine its trigonometric Fourier series. Mathematically, this signal can be represented as xt is equal to t upon pi, where t ranges from minus pi to plus pi. Hence, the fundamental time period of this signal is 2 pi, and the angular frequency is given as omega naught is equal to 2 pi upon t, which is nothing but equal to 1. The trigonometric Fourier series representation of the signal xt is given as a0 plus summation k is equal to 1 to infinity ak cos of k omega naught t plus bk sin omega naught t. Here ak is equal to 1 upon t integration from 0 to t xt dt. If we put the value of xt and change the limits from minus pi to pi, we will get 1 upon 2 pi integration from minus pi to pi t upon pi dt. If we determine its integration and put the limits, we will find that a0 is equal to 0. Similarly, ak is given as 2 upon t integration from 0 to t xt cos of k omega naught t dt. Once again, let us put the value of xt and modify the limits accordingly. We will get 2 upon 2 pi integration minus pi to plus pi t upon pi cos of t dt. This integration contains two functions of time, therefore it can be solved by integration by parts given by this formula. Accordingly, we will get ak is equal to 1 upon pi square into 1 upon k square into cos of kt plus kt into sin of kt, where the limits are minus infinity to plus infinity. And if we put the limits and solve it further, we will get ak is equal to 0. This is an odd function, therefore ak comes out to be 0. Similarly, bk is equal to 2 upon t integration from 0 to t x of t sin of k omega naught t into dt. Now if we put the value of the xt and modify the limits accordingly, we will get 2 upon 2 pi integration from minus pi to plus pi t upon pi sin of kt dt. This is an integration that contains two functions of time, therefore we can solve this by integration by parts method given by this formula. Accordingly, we will get bk is equal to pi square into 1 upon k square sin of kt minus kt into cos of kt with the limits minus pi to plus pi. Now if we put the limits as minus pi and plus pi and solve it further, we will get bk is equal to 2 upon pi square k square sin of k pi minus 2 upon k pi into cos of k pi. Here sin of k pi is going to be 0 because k is an integer number. Similarly, cos of k pi will be either plus 1 or minus 1 depending upon the value of the k, which is now turning out to be 0 minus 1 upon k pi into minus 1 raised to power k. If we take this minus with this power, we will get bk is equal to 1 upon k pi into minus 1 raised to power k plus 1. For putting the coefficients in the trigonometric series, we will get xt is equal to summation k 1 to infinity 1 upon k pi minus 1 raised to power k plus 1 sin of k omega naught t. This is a trigonometric Fourier series representation of the Sawtooth waveform given by xt. Now let us derive the exponential form of Fourier series from its trigonometric form. Trigonometric form is given as xt is equal to a naught plus summation k is equal to 1 to infinity ak cos of k omega naught t plus bk sin of k omega naught t, where ak is equal to 1 upon t integration 0 to t xt dt and ak is given as 2 upon t integration 0 to t xt cos of k omega naught t dt. Similarly, bk is equal to 2 upon t integration 0 to t xt sin of k omega naught t dt. Since cos of k omega naught t is equal to e raised to power j omega naught t plus e raised to power minus j omega naught t upon 2. Similarly, cos of k omega naught t is equal to e raised to power plus j k omega naught t minus e raised to power minus j k omega naught t upon 2j. If we put the value of the cos of k omega naught t and sin of k omega naught t in this equation, we will get xt is equal to a naught plus summation from k is equal to 1 to infinity ak 1 upon 2 into e raised to power j k omega naught t plus e raised to power minus j k omega naught t plus bk into 1 upon 2j e raised to power j k omega naught t minus e raised to power minus j k omega naught t. If we further solve this and segregate the terms, we will get xt is equal to a naught plus summation k is equal to 1 to infinity ak minus j bk upon 2 into e raised to power j k omega naught t plus ak plus j bk upon 2 into e raised to power j k omega naught t. Further, xt is equal to f naught plus summation k is equal to 1 to infinity f k e raised to power j k omega naught t plus summation 1 to infinity f k conjugate e raised to power minus j k omega naught t, where f naught is equal to a naught, f is equal to ak minus j bk upon 2, and fk conjugate is equal to ak plus j bk upon 2. After rearrangement of the limits, we can write xt is equal to f naught plus summation from k is equal to 1 to infinity fk into e raised to power jk omega naught t plus summation from k is equal to minus 1 to minus infinity f minus k conjugate into e raised to power plus jk omega naught t. If we combine all these three terms, we will get xt is equal to summation from k is equal to minus infinity to plus infinity fk into e raised to power plus jk omega naught t, where fk is given as 1 upon 2 into ak minus jbk. If we put the value of the ak and bk, we will get 1 upon 2 into 2 upon t integration from 0 to t xt cos of k omega naught t into dt minus j 2 upon t integration from 0 to t xt sin of k omega naught t dt. On simplification, we will get fk is equal to 1 upon t integration from 0 to t xt cos of k omega naught t minus j sin of k omega naught t, which further can be written as fk is equal to 1 upon t integration from 0 to t xt into e raised to power minus j k omega naught t dt, which is further equal to f minus k conjugate. In radian form, this fk can be written as 1 upon 2 pi integration from 0 to 2 pi x function of omega naught t into e raised to power minus j k omega naught t d omega naught t. Now let us consider one practice problem from the previous examination, where we are given a train of pulses of time period t and the pulse width is tau. This signal can be written mathematically as xt is equal to a from t is equal to minus tau by 2 to tau by 2 and 0 otherwise. Fourier series is given as fk is equal to 1 upon t integration from minus t by 2 to plus t by 2 xt into e raised to power minus j k omega naught t into dt. Now let us put the value of the xt in this relation. We will get 1 upon t integration from minus tau by 2 to plus tau by 2 a into e raised to power minus j k omega naught t into dt. If we integrate and put the limits of t, we will get fk is equal to 2a upon t k omega naught into e raised to power plus j k omega naught tau by 2 minus e raised to power minus j k omega naught tau by 2 upon 2j. Further, fk is equal to 2a into tau by 2 divided by t sin of k omega naught tau by 2 divided by k omega naught tau by 2, which is nothing but a Sinc function. We will write fk is equal to a tau by t Sinc of k omega naught tau by 2. Sinc function is one of the important signals in communication systems, and this is also known as a sampling function, which is defined as sin of theta upon theta. If we plot this, we get an even function as shown in this figure with a unity area. The magnitude of this signal crosses 0 when theta is equal to plus minus pi, plus minus 2 pi and so on, but it reaches the maximum value of 1 when theta is equal to 0. Now let us plot fk is equal to a tau by t Sinc of k omega naught tau by 2. Here fk's are impulses over the axis of frequency omega, and these fk's are separated by the omega naught, which is equal to 2 pi upon t, and this is the frequency spectrum of the signal, which is a train of pulses in time domain. It is often easier to analyze signals and systems in terms of their spectral representations. A Fourier series representation of a continuous time signal xt is a summation of infinite number of sinusoids whose angular frequencies are omega naught, 2 omega naught, 3 omega naught and so on. This was given by the relation xt is equal to summation from k is equal to minus infinity to plus infinity fk into e raised to power plus j k omega naught into t, where fk's are complex numbers having particular amplitude and phase, which is given as fk is equal to 1 upon t integration from 0 to t xt into e raised to power minus j k omega naught t into dt. Amplitude and phase spectrum of a continuous time signal is a discrete spectrum due to the integer values of fk, which is equal to 1, 2, 3, 4 and till infinity. For example, fk given by the previous numerical problem is equal to a tau by t sinc of k omega naught tau by 2. If we plot amplitude of the fk with respect to omega, this is known as amplitude spectrum of the signal, and if we plot phase of the fk with respect to omega, this is known as the phase spectrum of the signal. Here is an important concept known as Gibb's phenomena. According to Gibb's phenomena, original signal xt can be recovered from the addition of all Fourier series components. Overshoots will appear around the edges and overshoot will get sharpened with increasing number of the Fourier series components. The dampings will reduce with increasing number of Fourier series components, and the overshoots will remain around 10% of the amplitude of the signal, and it will be irrespective of the number of the Fourier series terms. Now let us conclude this video by floating some more questions from examination point of view for the practice of the students. These questions are classified as lower order thinking skill based questions and higher order thinking skill based questions. Higher order thinking skill based questions usually involve determination of the solution to some numerical problems, and it is my personal request to the student that they must solve these numerical problems so that they can get good grip of the subject. Dear students, in the next video we will cover properties of Fourier transform. Till then, keep learning, keep sharing.